Okay, lecture 2.3. That is not a trend, don't expect that to happen. All right, limit of a function at a point.
Wait, is that really it?
Yeah, that's it. That's to motivate the next one. Limit of a function at a point. Okay? All right, what did we talk about last time? We talked about limits of sequences. Yeah, now we're going to talk about limits of functions at a point. Okay? So first we're going to try to motivate this again with that example, so I'll bore you to tears again with that example. Then we'll define the limit, we'll find some limits, we'll talk about discontinuities, and then we'll talk about infinities and asymptotes. Okay? And then we'll talk about limit laws and do some examples. Okay? This one's substantially longer than the last one. Nice breakable long chunk. Okay, recall the ball drop example from last lecture. Okay, what did we look at? For that guy, again, what did we do? We looked at, consider, the average velocity on the time interval from t equals 3 seconds to t equals, okay, I'm going to take out the units, okay, to make this nicer. To t equals 3 plus delta t. Which is this thing, right? Okay, again, the average velocity on the time interval from t equals 3 to t equals 3 plus delta t, with delta t afterward, and we got the slope of this secant. So let's write it out this time, instead of getting the computer to do it. Okay, average velocity for any time interval starting at 3 is equal to the change in position. So y at 3 plus delta t minus y at 3 divided by delta t, the length of the interval. Okay? Okay, now we chuck those into that equation. You get this thing. 150, the height of orthunk. Minus 4.9 times 3 plus delta t squared. Okay, that's that guy. Minus y at 3. 150 minus 4.9 times 3 squared. Over delta t. You see where I got that from? Yeah. Where I got that from? I plugged it into the physics equation there. Okay, that's it. Does that make sense? That's all. Thank you. Okay? All right, I can clear the brackets and do wonderful things. 150 and 150 get rid of each other. And we get left with minus 4.9 times 3 plus, you can skip steps here if you like, minus 3 squared over delta t. All right? You can do whatever you want. You can expand this and clear stuff, or you can do difference of squares, which is what I'll do.
Bend the knee.
While showing the board respect. 3 plus delta t minus 3. And 3 plus delta t plus 3. Over delta t. Okay, 3 plus delta t minus 3 is just delta t. So I got minus 4.9 times delta t times 6 plus delta t all over delta t. Okay? Here we did it properly. Minus 4.9 delta t 6 plus delta t over delta t. Okay. Where is that guy not defined? Right? 0. You can't divide by 0, which is the problem we had there. Okay? That's why that hole's there. Okay? So, this thing, its domain is everywhere except for 0. Okay? So that thing is undefined at 0. Undefined at 0. Elsewhere, it's equal to what? When delta t is not 0, just cancel out delta t, and you're left with minus 4.9 times 6 plus delta t. Okay, and this works if delta t is positive or negative. Okay? Okay, so you can approach the tangent from both sides with the secant. Questions yet? Okay. What is that? That's just the equation of that line. Okay? And again, valid everywhere except there. Okay. So the instantaneous velocity at 3 seconds, the instantaneous velocity at 3 seconds is just the value that fills that hole. Okay? It's just what this function would have been if it was a reasonable, nice function and it was defined there. Okay? It's the value you approach as you approach 0 from both sides. Okay? And what's that? Minus 4.9, 6 plus 0. Minus 29.4 meters per second. Okay? That's the value that fills the hole. Just one sec. That's the value that fills the hole, and it's the limiting value of the average velocity as you decrease that time interval. Does that make sense? Okay, so literally what the graph did, now we just did it on the board. Okay, and again, this is not a matter of just plugging delta t into this. That's not what this was. This thing isn't defined at delta t. It's defined everywhere. Plugging 0 into this as delta t. This thing isn't defined at 0. Okay, it's defined everywhere else. So what we have to do is we have to see what we approach as delta t approaches 0. What was your question?
I was just asking if this like, it looks like first principles because like, it's not first principles because like
The derivative first principles thing?
because like you got like the elsewhere u equal to negative 4.9 and blah blah blah. That's like the
It should look a lot like the first principles derivative thing.
okay.
Yeah.
But it's not, right?
It's essentially what it is, right? It's a difference quotient. If that was h and that was h and that was x and that was x, it would look an awful lot like the difference quotient that you're probably used to. And if I put a lim in front, then it's exactly what you're used to, right? The first principles derivative thing?
Yeah.
It should look a lot like it. A lot like
And
it.
that's why we got the instant velocity like function.
Yes, except only evaluated at 3.
Oh,
Okay.
So this thing was specific to 3.
that's the difference.
Yeah.
Okay.
Yeah, what's the difference? We only did it at a point, and I didn't write lim everywhere, and I didn't mention the derivative. This is essentially exactly the same as what you're thinking. Okay? Again, this is at a point, yes.
Can you please explain how did you get the instant velocity
There.
from the average velocity?
Okay, so, like I said, as we bring this guy closer and closer in, the secants get closer to the tangent. The average velocity gets closer to what we think should be the instantaneous velocity. So as we bring delta t in, we expect the average velocity to converge to something. And that something isn't that hole, but we can fill in that hole reasonably with that, okay? By seeing what this would have been if it was defined there, reasonably. Okay? So we just put 0 into the equation we have. And that's it.
No, how did you get that value minus 20?
I plugged 0 into that. That's it. 0 is delta t. Again, you're not plugging 0 into this, you're plugging 0 into this, okay? To see what it would have been if it were defined there. Okay? Does that make sense or no? I'm assuming yes. Until someone says it. Okay. If you don't like the delta t thing, instead you can do this. I just wrote this up, I won't go through it. You can look at this if you prefer this. You could look at times from 3 to t star, okay? And instead of bringing delta t down to 0, you bring t star closer and closer to 3, okay? And there's the math for you, and that's what that graph looks like. And the whole now is at t star equals 3, and that's the whole you have to fill in, okay? And if you've looked at derivatives, you'll remember that there's two sort of versions-ish of the definition of the derivative. That's all that is. Okay, you either shrink the interval down, or you bring the end of the secant, the other point involved in the secant, closer and closer to the point that you care about. Any questions? It's just something I say a lot.
How did you get from the bracket 3 plus
There?
yeah to the next one?
Difference of squares?
Okay.
Yeah, a squared minus b squared is a minus b times a plus b. Or expand this, and the 9s will go away and go, yeah. Okay? I thought this was cuter. Okay, so whenever we have an instantaneous rate of change question, we have to do something like that. We have to come up with something that looks like this. And again, this particular function is specific to time 3. We could do the same thing for any other instant that we care about. Okay? Whenever we want to answer a question like this, we come up with something like this, and we have to look at a limiting value like that, and we have to try to fill in a hole. Okay? And the distance of finding limiting values and filling in holes is the limit. Okay? And there's the definition of the limit. The limit of a function at a point. If f at x approaches L as x approaches a, we write f at x approaches L as x approaches a. Or the limit of, ooh, look, it's underneath as well. The limit of f at x as x approaches a is equal to L. Okay? So this thing we've kind of been talking about the whole time, now we have it spelled out there. Okay? So for our example, our instantaneous velocity at time 3 is just the limit as delta t shrinks down to 0 of the average velocity evaluated using delta t. Okay? Okay, and if you like the t star version, you'd be taking the limit as t star goes to 3. All right, so oversized picture. You're supposed to have the graph of a function. Okay, that's our point A. If as we approach A, our function approaches some value L, then we say that the limit as x approaches A of f is equal to L. Okay? There could be a hole there. It could be filled there. This point could be somewhere else. It doesn't matter. Okay? The question is, what are you approaching? Okay, so technically what matters is the behavior of f in the neighborhood of A. Not at A, never at A. Only in the neighborhood of A as you're approaching A. Okay? Okay, if you care about the technical definitions of these things, because that's a ludicrously sloppy definition, okay? So the technical definition will be closer to something like this. This being the limit means that for any band, okay, as narrow as you like, around L, I can get the function to live inside that band if I pick values of x close enough to A but not equal to A. Okay? Maybe that makes sense. Okay? But again, that's close to the technical definition with deltas and epsilons if you've seen that thing. Okay? Yeah. Yes, I can, and you don't need to know that, okay? Okay, so you can get the function to live within as narrow a band as you want around the limit by picking x values sufficiently close to A but not equal to A. Okay? That's the technical way to think about it rather than that sloppy thing. Okay? If you want to prove anything, you need the technical definition. Okay? But again, that's all you really need. Okay. All right. We talked about the limit of a sequence before. How is this different? We're now talking about general functions. And also, we're now talking about x approaching a point A. We're not talking about n blowing up to infinity. Okay? Quote unquote infinity. Those are the differences. Okay? So x is approaching a point, and we're talking about general functions, not sequences. All right, if you questions? Okay. And when we talk about the derivative, you will see this almost exactly again. Example. Again, very similar to what we had. Suppose we have f at x equal to x squared minus 4 over x minus 2. Okay, and I want you to tell me what happens as x approaches 1. Anyone know? Or what would you do?
Just sub it in.
You could just sub it in. Yeah. Okay. Now, let's see what this thing is. Okay, again, difference of squares, let me write it like this. X plus 2, x minus 2 over x minus 2. Okay? Undefined at x equals 2, because that'd be division by 2. So this is undefined at x equals 2. But elsewhere, it's just, these guys would just cancel and you get x plus 2. Okay? Alright, so what does that look like? Something like that. Okay, except at 2. And we have a hole there. Okay? It looks like x plus 2, except at 2 where you've got a hole. Okay? Okay. Now as x approaches 1, okay, as x approaches 1, the function approaches 3. Okay? So yes, that limit exists. The limit as x approaches 1 of f at x is just 3, okay? Which you could have gotten from plugging in to here or plugging into here, okay? And the reason it works is because the function is nice there, okay? Or continuous there, a word which we'll talk about more later, okay? Function's continuous at 1, and so we could have just plugged in, okay? But it's important to know what we're talking about. We want to know where the function is going, not where it's at, where it's going as you approach 1, okay? And the answer is 3. Okay, what happens as x approaches 2? Is there a limit, and what is the limit? Limit's 4, okay? Okay, as x approaches 2, the function approaches 4. Okay, that's it. Even though it's not defined there. Okay? It doesn't matter what's going on at 2, it matters what's going on as you approach 2. And you could have gotten that by plugging into this, right? Which is the equation of the full complete line, the one that fills the hole. But you could not have gotten it by plugging into this, because this guy is not valid at 2. Okay?
So initially, like right now, we pretend to not know the rest of the derivatives.
You pretend to not know the word derivative.
Or that too.
You have no idea what that is yet.
Like we first, like we see this and they ask for the limit, you first try to factor it
Yeah, I mean, if it, yeah.
that way, and then like.
You want to know what it looks like. The point of this was to find out what this thing looks like, where its holes are, okay? And so then I can say, okay, at 1 there's no holes, everything's nice. I can just plug in and I'll see what this looks like, okay? At something like 2 where there is a hole, I have to fill in the hole, okay? And the thing that fills in the hole is this, so I could plug into this. That's it. Or look at what the curve looks like as you get closer and closer to that. Okay? Yeah, derivatives don't exist yet. And complex numbers don't exist, period. Okay? Imaginary numbers don't exist. In this course. Okay, good? Alright, so if I had redefined this thing so that f at x was, if I said this, f at x is equal to x plus 2 for x not equal to 2, and f at x equals pi for x equals 2. Okay? So if I redefine this so that that guy, okay, here we had pi, the answer would not change. Okay? Nothing changes. Alright? It does not matter what value you take here. It matters what value you approach. Okay? So nothing changes. Does that make sense? Okay? So it doesn't matter if it's just a hole there or a hole with a point defined somewhere else. The limit's the same. care where we're going, not where we get to. Okay? Questions? You don't really want to use the derivative of something like that. Okay. You see this? No, you can't see this. You can't see that. Okay, discontinuities. What do you mean discontinuities? We haven't talked about continuities. Right. That's how organized this is. Discontinuities. Okay, again, we'll talk about what continuous means next lecture, whenever that is. Okay? But this is simple enough to understand, and a lot of you probably know what continuous means anyway, so let's talk about discontinuities. What's this? It's a break. Okay, a discontinuity is a break in the graph of a function. Okay? It's a point that as you try to trace out the function, you have to lift your pen from the paper to keep tracing. Okay? A break. Okay? And there's three types we'll talk about, and another type I'll refer to at some point later. Okay, so types of discontinuities. 1, removable. Okay? What is that? It means just a hole. Okay, here's an example. This is sine x over x. Okay? Alright. This guy is not defined at 0 because you'd be dividing by 0. Okay? So the domain is everything except for 0. So you've got a hole there. Okay, and it's a break, right? If I tried to trace this thing out, I have to lift the pen from the paper to keep going. Okay, just a hole in the graph. And we also saw this what before with the instantaneous velocity stuff. And you'll always see it with instantaneous rates of change. Why is it removable? Because it can be removed or fixed by assigning or reassigning f at a to be the limit as x approaches a of f. Whoa. Okay, so if you've got a hole at x equals a, okay, you can fix the removable discontinuity by either assigning or reassigning f at a to be the proper limit. Okay? So for instance here, what would reasonably fill in that hole? 1, okay, which is a magical fact right now, and we may talk about it later. Why? Okay, so if I put 1 in here, it would fix this, right? There wouldn't be a discontinuity there anymore. Okay? Fixed by reassigning. F at a equals the limit as you approach a. In this case, a is 0, and the filling value would be 1. Okay? It's removable. You can get rid of it by reassigning the function at a point. Does that make sense? Okay. Okay. So what did you say in this case? We said the limit as x approaches 0 from either side of f of x for that example. Sine x over x equals 1. Okay? Well, we have a removable discontinuity. At x equals 0. Which could be fixed by repairing the function like this. I'm just going to kneel now. Good. Okay. We'll keep the function definition everywhere except 0. And at 0, we'll give it the value it quote-unquote should have. Okay? So again, how do you fix removable discontinuity? You fill in the hole. And that's it. And that makes it continuous. 1 second. There's no breaks anymore. Okay? And this repaired version is called the sinc function, okay, or the cardinal sine function, or the unnormalized cardinal sine function, okay, which is a precious thing to you if you're into signal processing and you want to repair a signal from the samples from the signal, or you want to filter stuff. Okay, yes, ma'am. You had a question?
I was just gonna ask.
What sinc was? Okay, it's the repaired version of sine x over x. You fill in the hole, and you've now got a discontinuity anymore. Okay. Related to this fact is this fact. Sine theta is close to theta for small theta. You may have seen this before. Okay, when x is small, sine x, when you're talking about radians, please only talk about radians, is close to, so sine x over x is close to 1. Sine x is close to x when x is small. Okay? And that approximation is helpful in physics. For instance, when you're talking about the period of a pendulum or you're writing the equations for a pendulum, the small angle approximation is useful. Yes, you don't need to know.
How can sine 0 be equal to 1? Sine 0 is 0, right?
Sine 0 is 0, but you're also dividing by 0, bad, right? So it's just not defined there. So you need another clever way of seeing what you're approaching. It's not the value you have, it's the value you're approaching. Okay? And you can repair it by filling in the hole like so. Thank you, ladies and gentlemen. I'll see you on Friday. Okay, we talked about function limits, or we began to talk about function limits, and we will continue doing that. We were in the middle of discontinuities. Yeah, we talked about types of discontinuities, and the discontinuity is a break in the graph of a function. Called 2.3.
Oh, okay. Thank you.
Yeah. Okay? And this is a break in the graph of a function. It's a place where you have to lift your pen up to carry on tracing the graph. Maybe too loud. Okay, we talked about types. And the first one was removable, which I'm now spelling both ways because I think there's probably not any either. And this is just a hole, yeah, like that thing. And like the thing we came across when we talked about dropping the ball. And like the x squared minus 4 over x minus 2 example. Okay? So all those things had a hole, and you could get rid of the discontinuity of the break by just filling it in with the appropriate limit. Okay? So in this case, the limit does exist. Okay? It's just that there's a break there. Okay. Okay, so the second type now, jump discontinuities. We didn't do this, right? No. Okay. Okay, jump discontinuities. Example, the Heaviside step function. Y, x, whole, O. That's at 1. This is the Heaviside step function. Okay, there's a jump. Okay, and all step functions have jump discontinuities. So what is a jump discontinuity? F at x approaches different values, or limits. Let's say different values. From either side of x equals a, where a is where the discontinuity is. Okay? We're approaching different values from either side. Okay, so does the limit exist at 0? No, we're not approaching a single value, yeah, as we come in. Okay, so the limit doesn't exist. For that guy, the limit did exist. For this guy, the limit doesn't exist. The limit does not exist there. Okay? And if you want to talk about the technical definition or what that means, just ask me and I'll show you. Okay, so in terms of the technical definition of the limit, why is there no limit there? Okay. So we need to talk about one-sided limits. There we go. Okay. If f at x approaches L as x approaches a from the left, that is, for values of x less than a, we write that, and we say that the left-hand limit of f at x as x approaches a, or the limit of f at x as x approaches a from the left is equal to L. Okay? So for this guy, as I approach 0 from the left, the limiting value is 0. So for this guy, as I approach 0 from the left, I'm approaching 0. Yep. Alright, a similar kind of thing for the right. Okay, every time I said left, make it right. Every time I said less than, make it greater than, and change that minus sign there to a plus. Okay? So where it is in the notation, if there's a minus sign there, it means from the left. If there's a plus sign there, it means from the right. And there's a minus. Okay? Alright. And for this guy, the limit, as x approaches 0 from the right, as x approaches 0 from the right, the function approaches 1. Okay, that's as simple as these jump guys get. Okay? Okay. And we may have talked about this as a switch. It makes sense that this is a switch. And if you like electric circuits and for some reason you're here, when you flip the switch and the voltage source gets applied, you can think of this as the voltage getting applied at time 0, which is something I saw a lot. Okay? Okay. These one-sided limits disagree, so the limit, okay, the two-sided limit, quote unquote, doesn't exist. Okay? These disagree. So, the limit as x approaches 0 from either side doesn't exist, as we talked about before. Does not exist. Okay? For you to have a limit, you have to approach the same value from both sides. Alright. And in general, the limit as x approaches whatever a of a function f at x is equal to L if and only if the limits from the left and right are also L. Okay, the limit is L if and only if the limits, the one-sided limits are equal and equal to L. Okay? Does that make sense? And for all the guys we talked about, where we talked about limits, yeah, you could approach it from either side separately if you felt sufficiently sensitive. Okay? Make sense? Alright. Alright. Next up. Infinite discontinuities. I'm just going to say this. People do problems, okay? Don't just rely on having seen me do things, okay? That's all. Don't just read solutions. Don't just watch people. Please, please, please do problems. Okay. That was a bit out of place. Okay, here's a function. Y equals 1 over x squared. Looks roughly like that. Okay? And what's happening? This guy is growing without bound on both sides of 0, okay, as we approach 0. Okay, so as we get closer and closer to 0, this guy is growing without bound. And that's what infinite discontinuity is. The function grows or falls without bound approaches A, the point of the discontinuity, from at least one side. Okay? That's what's happening here. In fact, from both sides. As you approach 0 and x, the function is growing without bound. Okay, does the limit exist? Say no loudly. Thank you. Okay? Those who thought the limit exists, what would you say? Infinity or something, right? Is that what, okay, so as we approach 0, you want to say the limit's infinity, don't say that, okay? The limit does not exist, okay? We're not approaching a single number. As we come in, the function is not approaching a single value. Okay, it's just blowing up. Okay, there's no limit. Okay? The limit does not exist there. Again, because to have a limit, you have to approach a single value and the same one for both sides. Yes, ma'am?
So in such a case, asymptotes always exist.
Asymptotes?
Always exist. So if you're talking about infinite limit.
Yes, and there's a
Yeah.
few slides away. Yeah, that's it. Okay, so we say limit exists if we're approaching the same value from either side and it's a number, okay? Okay, so the limit does not exist there because we're blowing up and we're not approaching a single value. Okay, and remember again, for the removal guys, the limit did exist. For this guy and the jump, it did not exist. There we go. Infinite limits, and that's what this guy is. If f at x increases without bound as x approaches a, we write that. And if f at x decreases without bound as x approaches a, we write that. Okay, and you can write one-sided versions of this. So blowing up as you approach from the left, or blowing up or down as you approach from the right. And those are defined as expected. Okay? Questions?
Yeah.
Yeah.
If
I'm about to write that here.
If it's at limit x approaches 5 plus on the graph, what would the answer be?
Here?
Like, yeah,
5 plus?
yeah.
What was it?
So would it
1
be-
over 25? 5? Yeah, so 5's like there,
Yeah.
and you get a 1 over 25.
So what?
As you approach from the right, the function approaches 1 over 25. Yeah? Does that make sense?
Would it be like positive infinity? Because
You're saying 0, right? You're approaching 0 or 5?
I mean, like, I don't know. It was a question on the Mobius.
Uh-huh.
It said like limit x approaches 5 plus, and then you have to like find from the graph.
Yes. You want to show me?
Yeah, I'll show
Yeah,
you.
you show me. I'll tell you. I mean, I won't tell you. I'll help.
I already.
Yes. Either way. Okay? Alright. And we talked about this kind of thing for sequences, right? We talked about sequences blowing up. This is the same sort of deal, except it's for a general function, and it's at a point, not at infinity. Cool. Okay, does this make sense? Again, these guys do not exist, okay? These limits don't exist. This is just a particular way in which they don't exist, okay? The blowing up or blowing down way is a particular way in which limits don't exist, okay? Alright. And for instance, for this guy, what do we say? We say the limit as x approaches 0 from either side of 1 over x squared, we write infinity, okay? Because it grows without bound from either side, okay? The left hand limit at 0 and the right hand limit at 0, you could also write that, okay? So you write x approaching 0 minus that, x approaching 0 plus that, or x approaching 0 that. Okay? This approaches the same thing for both sides. Or doesn't approach anything for both sides in the same way. And again, I don't know if you guys care about technical definitions. If you care, you can talk to me and I'll tell you how that works for this kind of thing. Okay? Or just ask them here now. Questions now? Does this make sense? They don't exist, but they don't exist in a special kind of way, the blowing up or blowing down kind of way. Okay. Okay, another example. look at the function minus 1 over x minus 2 plus 1. Okay? And if you like sketching stuff, what is that? That's sort of 1 over x looks like that. And we need to flip it, and we need to shift it right 2 and up 1. So the asymptote goes there, asymptote goes there. That's 1, that's 2. And it's flipped, so it looks sort of like that-ish. Okay, again, 1 over x would have looked like that. We have to flip it, because of that minus sign, shift right 2 and up 1, right 2, up 1. Okay? Okay, what is the limit as we approach 2 from the left? Yeah, you'd write positive infinity. And if you want to be really nice, you say the limit doesn't exist, but we write that first one. Except the one-sided version. So, for this guy, we say the limit as x approaches 2 from the left. As x approaches 2 from the left, this guy blows up. Okay? It increases without bound. So we write that. Okay? From the left, blows up. Okay, or you can think, okay, what happens if I have a number that's just under 2? Okay, if I have a number that's just under 2, this guy is a tiny negative number. This guy is a huge negative number. This guy is a huge positive number, and the whole thing is a huge positive number, so it makes sense that it blows up. Okay? From the other side, from the right, we write minus infinity. Because as we approach 2 from the right, it blows down. Decreases without bound. Okay? Okay? Alright. Plus, minus. Okay, so what do I say about the limit as x approaches 2? Doesn't exist, period. Okay? None of these limits exist. Okay? That limit doesn't exist. Okay? But these guys don't exist in a special way. These guys blow up, this one decreases without bound, and this we can't say anything because it behaves differently on either side, okay? So we just say it doesn't exist and that's the best we can do.
And there's also an asymptote too. Well, like,
Yes, that is possibly the next line. Yeah. Okay? Good? Alright. Right, the reason we could write this for the two-sided limit was because it behaved the same way on both sides. It blew up on both sides. Alright. Okay, and incidentally, that thing I wrote here and in tutorial at some point about what happens if you have a constant up top and on the bottom something that approaches 0 and how that blows up, this is what that is. Okay? So if you got a positive constant up top and on the bottom something that's positive but goes to 0, then the whole thing blows up to infinity. Okay? And if you got a negative constant over that, then it goes to minus infinity. And if you got a positive constant and this guy is negative and goes to 0, then you've got divergence to minus infinity. Okay? If you have a positive constant and you divide by a positive thing, that shrinks down to 0. Okay, you got a positive thing divided by a positive constant divided by some positive thing that shrinks down to 0. This thing blows up. And if you have a positive constant over a negative thing that goes to 0, or the constant over a negative thing that goes to 0, then that thing blows down. Okay, that's it. Does that make sense? In case you come across that, which I'm guessing you will at some point. Hey, look at that. Hey people, what's this line called? Yeah, vertical asymptote. Okay, this is a big deal when you're sketching, yeah? Vertical asymptotes. The vertical line x equals a is called the vertical asymptote of the curve y equals f of x if at least one of the following is true. From one of the two sides at least, it either blows up or decreases without bound. Okay? So for this guy, we have a vertical asymptote at x equals a. At x equals 0. So this guy has a vertical asymptote at x equals 0. This guy, okay, because in fact on both sides, it's blowing up, okay, the function. Over here, we have a vertical asymptote at x equals 2. This guy, because on this side it's blowing up and on this side it's decreasing without bound. Okay? One side is enough. If it blows up or blows down on one side, that's good enough. Okay? Y equals, okay, y equals ln x, or log base e of x. Vertical asymptote are known until where? One number will do it. Thank you. Excellent. Okay? Excellent. Okay, so this guy looks like that. Okay, and just going like that. Okay. So that's what that looks like. We have a vertical asymptote there. Vertical asymptote at x equals 0. Because what? The limit as x approaches 0 from the right doesn't exist in this special way. Okay? As we approach 0 from the right in x, y, the function decreases without bound, so we write that. Okay? The limit from the left does not exist. The function doesn't even exist there. There's no limit from the left. So there's no two-sided limit. Okay? And you can also think about things like the tangent, the cotangent, the secant, the cosecant, and then see what do sine and cosine do as you approach various values from either side. Okay? And how do those functions blow up or blow down? Okay? Questions? I suspect that thing I'm saying is not a technical term. So if you want people to respect you, say decrease without bound rather than blow down. Okay? All right. What's going on here? As I go that way. We've got another kind of thing. We've got a kind of settling. Yeah, so we need to talk about that as well. So, we want to talk about what functions do as x gets very large or very large negative. So we talk about limits at infinity. If f at x approaches a number L as x increases without bound, we write that. If x approaches a number L as x decreases without bound, we write that. Okay? Last one was infinite limits, blowing up or blowing down. Now we're talking about limits at infinity. So what happens if you go that way a lot or that way a lot?
And behaviors?
Hmm?
Are they behaviors? And behaviors?
Yeah, pretty much. Yeah. I wouldn't say n because you never get there. Okay, and we talked about this with sequences. This is similar-ish to sequences, right? We talked about n going to infinity, quote unquote. This is similar to that, except with functions. Okay. Okay, so this is limited infinity. If you wanted a title on this bit, you could have called it vertical asymptotes and infinite limits. This is limited infinity. Okay, so for example, as x decreases without bound, what does e to the x do? Does that limit exist? Is it a nice number? What does that look like? It looks like this. Okay? And as x decreases without bound, this function is getting closer and closer and closer to 0. That limit exists and is 0. Okay? As x decreases without bound, as we go farther and farther left, we get closer and closer and closer to 0. The limit exists and is 0. And my usual refrain, if you want to hear about the technical definition, just ask me. Okay, and like she indicated, if you want to talk about long-term behavior or distant behavior, this is the kind of stuff you talk about. You want to talk about what happens if you go very far that way or very far that way. Okay? Okay, tell me if you got questions. Okay, we call this a vertical asymptote. What's this puppy called? Horizontal asymptote, and that's what these guys partner with. Okay? A horizontal line y equals L is called a horizontal asymptote of the curve y equals f at x if either going to the right without bound you hit a limit, or you approach a limit, or going to the left without bound you approach a limit. Okay? Horizontal asymptote here is y equals 0. I'm just going to be sloppy here. Horizontal asymptote at y equals 0. Okay? Because approaching, how about this? Decreasing x without bound takes you closer to it, and increasing x without bound takes you closer to it. Over here we have a horizontal asymptote at y equals 1. There. Because as I go further and further this way I get closer to it, and as I go further and further this way I get closer to it. Okay? Either one is enough. Yes, ma'am? Like this, how it's above? Yeah, no. Sometimes you wind up thinking about that stuff and writing things about it, but for this, no. Like would you write 0 plus or something on this side? No. No, the plus superscript and minus superscripts belong here. Yes, ma'am.
So essentially all these limits are like heading towards their asymptotes, but they never touch it.
You're predicting everything I'm about to say. Yeah, I'll talk about that in a second. Okay? So again, limits at infinity, if they exist, are horizontal asymptotes. Yeah? And again, in this case, it worked on both sides. It doesn't have to be so. And indeed, on this side, in this guy, you only approach it going this way. Okay? And in this case, you still have a horizontal asymptote at y equals 0. Because you approach it as you go this way. Okay? E to the minus x has the same horizontal asymptote, except it approaches it this way. Arctan, you may remember. The tangent function had vertical asymptotes. Okay, quite a lot of them. Two of them were at x equals plus pi over 2 and x equals minus pi over 2. When we restricted and inverted, we got horizontal asymptotes for the arctan function. Okay? So for the arctan function, for example, or inverse tan. Okay, that guy has horizontal asymptotes at y equals pi over 2 and y equals minus pi over 2. Okay? Something like this. Okay? Pi over 2 minus pi over 2, and it approaches. Can the curve touch the asymptote? Yeah. Okay? Okay, the only requirement was that it approach it, okay? It's possible for it to cross it. So for example, if you have something like this, what do we got? Okay? We're approaching it, yeah? And we're getting closer and closer and closer to that line as we go further and further that way. That is still a horizontal asymptote, by that definition. Okay? You can touch it, you can equal it, you can do whatever you want. What matters is the limit has to be there. Yeah.
So like Is it only for horizontal asymptotes that we want to cross, or you're basically saying through that?
Yeah, think about what would happen if you started touching a vertical asymptote. Okay, to be able to cross one, you'd have to do this. That's not a function anymore. Okay, to be able to touch one and stay there, that's not a function anymore. Right? Yeah. You see what I'm saying?
Yeah.
Yeah, you got trouble with the function thing if you try to have a vertical one that you're touching a lot. Or at all. Okay? Anyway, that's the definition. Stick to the definition. It's not about not touching. It's about heading there. Okay. All right, look at this guy. What did that guy do? It approached 0 from both sides. Or to put it properly, as we go left, we approach 0, and as we go right, we approach 0. So, let's generalize that a bit. In fact, for any r greater than 0, and in that case was r equals 2, for any r greater than 0, the limit as x grows up of 1 over x to the r is 0. Okay? Like 1 over x squared. Like 1 over x. Okay? Try a few things in there and convince yourself that that makes sense. Okay? 1 over square root x. Whatever. Okay? As you make x bigger and bigger and bigger, the bottom gets bigger and bigger and bigger, and the whole thing just goes to nothing. Okay? And for any r greater than 0, this one's a bit sickening, such that x to the r is defined for all x. The limit as you go left is also 0. Okay, so we're saying as we make x bigger and bigger and bigger, this guy gets bigger and bigger and bigger, the whole thing gets smaller and smaller and smaller. Approaching 0. For this guy, we have to be careful because for some exponents, we're going to have a problem. Okay, so for instance, for square roots, right? So if this was 0.5, okay, that's not defined down there. Okay, so you don't want to be taking that kind of limit. Okay, so this is just to look after that. Okay, but for something like r equals 3 or r equals 1/3, this is perfectly valid. Okay? Basically the same deal. As this gets bigger in size, as x gets bigger in size, this guy gets bigger in size, this thing gets smaller in size and approaches 0. Okay, except you're playing with negative numbers there. Questions? Okay, if you want to see graphs of that, let me know. They'd be similar to the sort of sequence versions I showed you, because we had a similar thing for sequences. It'd be similar to that. Okay, here's an example. F of x equals 3x cubed plus x squared minus 2x plus 1 over, unnecessarily complicated, 2x cubed minus x squared minus 3. Okay, that might look familiar. We did a sequence like that. Okay? And you handle this exactly the same way. I'm not going to spell this one out. Okay? What do? You divide top and bottom by the highest power you see in the denominator. You divide the top and bottom by x cubed. Okay? So you're going to get on the top 3 plus 1 over x, blah, blah, blah. And over here, 2 minus 1 over x minus 3 over x cubed. Okay? Again, you have this. You have the sequence version of this. Just look at that. This is exactly the same approach. Okay? And what happens? All those 1 over x's and 1 over x squareds and 1 over x cubes die away because of that. Okay? And you just get left with 3 over 2. Just as before. Okay? And this time we can also talk about what happens as x decreases without bound. That limit is also 3 over 2 for the same reason. Okay? Because going that way, those guys also shrink down to nothing, leaving us with just 3 over 2. Okay? Yes?
Can you repeat the last part when you were explaining?
The negative one?
Yeah, the negative.
Yeah, okay. So again, you do the same trick. You divide through by the highest power in the denominator. And you get left over here with 3, 1 over x, minus 2 over x squared, 1 over x cubed, minus 3 over x cubed, minus 1 over x, and 2. And all those guys disappear because of this thing.
How does that apply to this?
Okay, this is x going to minus infinity for 1 over x to the something positive. Okay? Those are going to be 1 over x, 1 over x squared, all those kinds of, those guys are all going to disappear.
Okay.
And all those kinds of guys are defined for all x.
So it doesn't matter if x approaches positive and your f is going to be 0.
It's going to be 0 provided that you have a friendly power. Okay? Okay. And again, unfriendly powers are things like square roots and things with even denominators in the exponents. Okay? Or irrational exponents, which I was trying to figure out. Okay? So if you've got a nice, well-behaved thing, and it's not one of those square rooty type things, you'll have something like this. Okay? And we didn't talk about this for sequences, we only went that way. Okay. Alright, again, look at what you did there, and same deal, okay? And to do this properly, very properly, you can use the limit law. Okay, so that guy, so the graph of y equals fx has a horizontal asymptote at y equals 3 over 2. From both sides, it approaches 3 over 2. Ta-da! Okay? Which, yes, is suspiciously just the quotient of the leading coefficients there. Okay, any questions or doubts about this? I have no idea if I'm going too fast or too slow. Any questions? Okay. All right. That's almost everything. Don't get excited. Almost everything for that part of this lecture. We didn't talk about one more thing, and that's the sort of equivalent of the sequence divergence thing, right? We said the sequences can fail to converge if we go that way, okay? And we didn't talk about that yet, so this is that. Infinite limit at infinity, with heavy, heavy quotation marks around anything that says infinity. If f of x increases without bound as x increases without bound, we write that. Okay? For example, this guy. If you'd like these notes to be more linear, let me know. Okay? We talked about if we go this way, we shrink down to 0 or towards 0, hence this thing. But if we go this way, this thing blows up. It increases without bound as we go this way. Okay? Hence, as we go to the right, this guy increases, forgive me, without bound. Okay? And that's all that is. Again, that limit doesn't exist. That's a special way in which it doesn't exist. And you can do similar things with minus infinity. So you could talk about going to the left and blowing up, going to the right and blowing down, you put a minus there, going to the left and blowing down, you put a minus there and a minus there. Does that make sense? Okay. We're all right? Limit laws. Nice sounds, everybody. Okay. All right, we talked about the sequence ones. These are very similar. These ones are a bit different. They're not different, we just didn't include them for the sequences. So you've got to check that those limits of f and g exist. And then if c is a constant and n is a positive integer, you got all this stuff. So the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. The limit of a constant times a function is just a constant times the limit. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits. Do not divide by 0. Okay. The limit of a power. How do I want to say this? You can see that, right? I don't know how to describe it. There you go. Works for powers and roots as well. Okay? Be careful when you're dealing with roots. Okay, follow the rules. All right? And if you can't answer a question without following the rules, ask me. Okay? Okay, these are what you do to play with limits. Example. Someone really needs to lubricate that front row there. All right, let's do an example. The limit as h, to confuse everybody, and later on we'll see h. As h approaches 0 of 9 plus h minus 3 over h. Okay. Can we use the quotient rule? Not quotient rule, quotient law, whatever. Yes, no. Bad, we'd be dividing by 0. No. Okay? So don't try to do that. Okay, so you can't use the quotient law because we'd be dividing by 0. What can we do? What do we do when we see stuff like this? Do you remember something with the square root?
The 9 plus h.
Yeah, cool. Yeah, Concha, thank you. Excellent. Very good. Okay. Okay, we do this. And just for the record, as h is near 0, this guy is positive, so nothing weird's going to happen. Okay? You multiply top and bottom by the conjugate. Okay? And why can you do this? Because you're effectively just multiplying by 1. Okay? So don't just divide or multiply by whatever you want. Okay? If you do it to the top and bottom, you're okay. But don't just divide through by 3 and hope that that'll work. That's not how things work. Okay? If you divide top and bottom by the same thing, you'll be okay. Okay. Provided it's not 0. Okay. Difference of squares. 9 plus h square root squared is just going to be 9 plus h minus 9, which is 3 squared, over this side. Okay? Those 9s destroy each other on the top. Okay. That expression is not valid where? It's always the same number. Okay? That guy is not valid at 0. Okay? But we don't care. Limits don't care, right? Limits only care what goes on around 0, not at 0. Okay? Okay. Okay? We cancel the h. That's only valid if h is not 0. But the limit doesn't care what goes on at 0. It cares what goes. Oh man! It cares what goes on close to 0. Okay? So we're free to cancel. So we get that guy, and you can do the same kind of thing with that x squared minus 4 over x minus 2 thing we talked about, or that ball drop thing we talked about. Same kind of thing happens. Okay? We do a cancellation, and we can justify it like that because we only care what goes on near 0 or near the point of the limit. Okay, this guy. Now we can use the quotient law. Okay, what's the limit of 1 as anything happens? Okay, the top is boring. Okay, I use the quotient law. That's only valid if it turns out that this bottom wasn't 0. If it winds up being 0, this wasn't valid. Now we can use that sum thing. I will not be spelling it out like this every single time, I promise. Okay? All right. The limit as you do anything of a constant is just a constant. Okay? So this guy's just 3. Okay? This guy, we can use that last thing. Okay? check that condition is gonna hold, it better hold, okay? So check, if it doesn't hold, then you're screwed. Find another way you're not screwed, okay? Okay, so provided that condition holds, i.e. the limit of this guy as h approaches 0 is positive, we're cool. So for this guy, we can use that last rule to write it like this. Okay? Now if you're feeling patient, you bring this limit in here, apply it to both of those guys, and add those two limits. Okay? Ultimately what you get is 1 over square root of the limit of 9, which is just 9, plus the limit of h as h approaches 0, which is just 0, plus, sorry, I had a moment there, plus 3. Okay, everything checks out. This guy was positive, good. This whole bottom bit was non-zero, good. And all the limits existed, good. Okay, the square root of 9 is 3. 1 over 3 plus 3, 1 over 6. Okay? All right. Good? Questions? If you want me to super spell it out, I'll super spell it out. Okay. We'll do a few more things next time. I just want to introduce something. No. Who's seen this before? There's a series of cute names. Squeeze, pinching, sandwich theorem. Okay? Okay, so suppose you want to find the limit of g as x approaches a. Okay? If near a, you can find two functions that are above and below g. Okay? Nice and color-coded. Okay? If near a, you can find two functions that are above and below g that squeeze in toward a limit, then you can conclude that g has the same limit. Good? Does that make sense? Okay. The same thing works for one-sided limits. The same thing works for limits at infinity. Okay? So that a can be replaced by infinity or minus infinity, or by an a plus or an a minus. And hell, I've got time to do a quick example, so I'll do one. Quick example for that. Let's see what a minute can do, people. This is the squeeze theorem. I may do this or just introduce this. This is an example. Suppose we want to find that limit. Okay? Can we use the product law? No, otherwise why am I doing this? Right? That second guy, that limit doesn't exist. The limit of sine 1 over x as x approaches 0 doesn't exist. Okay? Because what happens, you get closer and closer to 0, this thing just oscillates faster and faster and faster. You don't get to a particular place as you get closer and closer to 0. Okay, this is a kind of different sort of discontinuity than what we talked about before. There's 3 types we'll talk about, and another type I'll refer to at some point later. It just oscillates too hard, too fast. It's not going anywhere as you approach 0. Okay? So that limit doesn't exist. And so we can't use the product law. 30 seconds, huh? We can't use the product law. What can we do? Signs are always bounded below by minus 1 and above by plus 1. Okay? X squared everywhere but 0 is going to be positive. I can multiply everything by x squared and not worry about having to flip any signs around. Hey, look what I've done. I put a function underneath this guy and a function above this guy, okay? Both of which approach 0 as x approaches 0. As x approaches 0, this guy goes towards 0. As x approaches 0, this guy goes towards 0. So we pinch this guy in. So this guy must approach 0. Even though that other guy didn't exist, we can pinch him in. Okay? And we get a limit for that weird guy of 0. Alright? Alright, we'll do some more stuff next week. You got any questions, talk to me. Have a wonderful, wonderful long weekend. Happy Thanksgiving.